So I should apologize in advance. So I changed a little bit my plan for the talk, which is why the title is not entirely determined in advance. But I decided that the title is this. I tried to make it very accessible also to graduate students who are maybe not working in geometry and so on. So I really try to include many people in the enjoyment of the talk. So what I want to do is to explore several aspects of a mental diagram. So what I mean is, I want to write for you, so this is just philosophy. It is a picture of some organizing mathematics. Explore aspects of the following triangle. So, as you will see, it is very broad, but eventually I will mean some very specific things. Here, on this corner, I want to put symplectic or algebraic geometry and topology. And here I want to put combinatorics. Okay. In particular, what I am hoping to do in the next 50 minutes is to give you at least a glimpse of at least one way in which these three vertices interact in a very beautiful way. So I want to talk about all three vertices as well as the edges on this triangle. So of course this is much too vague. So I now make a new diagram, a new triangle, where I make these words a little bit more specific, but they are representing this same diagram. So the motivating example, which I will use as an excuse to discuss some of these mathematics, is classical Schubert calculus. So when I say classical, I mean the following things. So here, in the algebra and representation theory, I would like to put the cohomology of the Grassmannian of k-planes in Cn, or possibly the cohomology ring of a certain variety, the 5 varieties in Cn. And sometimes I put this in parentheses because I don't know how much I can say about everything, but anyway, sometimes I put this in parentheses because sometimes I want to do ordinary cohomology, sometimes I will do equivariant, but let's not worry about that too much right now. And then there are certain classes inside of these rings, so certain elements of these rings, which are usually denoted sigma sub w. So these are called Schubert classes. So at the moment, please don't be alarmed if I am introducing many things you have not seen. We will talk about all of these, but I just want to put them on the board so we see them. So this is supposed to represent this vertex. Okay, and now over here I want to put, well, okay, so I have said the cohomology rings of some spaces. So of course here I'm going to put the actual spaces. So the Grassmannian of Kn, flags in Cn, and actually today I also will want in general to talk about, so this is standard symplectic geometric notation, so curly O sub lambda, these are coadjoint orbits of compact Lie groups. But anyway, and I also want to discuss things that are called Schubert varieties. Oh, I'm sorry, not lambda W, Schubert varieties. So this is the geometric characters that will appear in our play. Okay. All right, and then here, so what do I mean by combinatorics? That's a very large area of research, so what do I mean? I'm meaning something very specific. I want combinatorics of Varroa groups. Okay. So that's a little bit more specific as a triangle. And now let me say something about my title. So as Professor Sa said, I am trained originally as a symplectic geometer, although nowadays I do many other things. But anyway, that is my training. And so one of the goals for what I would like to communicate today is where is the symplectic geometry. So my first goal, which I would like to achieve, is to show you how to think about this from that symplectic point of view. So my goal number 1 now is to talk about this vertex and tell you why these are actually symplectic objects. And again, that will give me the excuse to actually, so I say that this is my goal, but it will give me the excuse to actually tell you about the other things as well. So let us proceed. Okay, so let me take a slight step away from this picture. I'll say something a little bit more general, but then we will come back to this. So this is a new object I want to do. So let me just denote by lambda some list, let's just say decreasing of real numbers. Okay, and I will interpret these as the eigenvalues of some Hermitian matrix. So let's let O sub lambda, that is traditional symplectic notation, but it is just fancy notation for a very simple object. I'm looking at n by n Hermitian matrices such that the spectrum of A, which is to say its eigenvalues, if I list the eigenvalues, it's just this list. So I'm sorry, this is bad. This is supposed to go there. Okay, so I'm just looking at a particular set of Hermitian matrices. So of course this lives inside the set of all n by n Hermitian matrices. That's a vector space. But instead of focusing on that, let me simply remind you from linear algebra that any Hermitian matrix is, of course, unitarily diagonalizable. Diagonalizable, in fact, to the diagonal matrix which has exactly these eigenvalues on the diagonal. So this is, in fact, equal to the set where I take G and I take the diagonal matrix with these eigenvalues, and then I just conjugate. Right? Okay, so that's the same thing. Okay, very good. But now if I think about what that is, well, I am saying that this unitary group acts on the set by conjugation, and I'm just looking at the orbits. So therefore, it acts transitively, and this is the same as the unitary group modulo the stabilizer of this particular diagonal matrix. Right? Now, of course, in the generic situation where all of these eigenvalues are distinct, the stabilizer will just be the usual diagonal torus sitting inside of the unitary group, but in general it could be larger. Never mind. I'm just saying that this is a homogeneous space of the unitary group. Okay, so there's already some geometry there. It's a homogeneous space of a Lie group. Okay, very good. So let's just assume for simplicity that, so starting now, let me assume that they're all distinct. Okay, and if I do that, then in fact I can continue this chain of isomorphisms. This is also the same thing as dln of C modulo the Borel subgroup, which is just the subgroup of upper triangular matrices. So it's anything it wants up here as long as it's invertible, and 0 below the diagonal. Okay, so what I'm trying to say here is this exhibits this O lambda as a complex manifold as well. Okay? Okay, very good. So, with that setup, let me ask the following question, which, again, if you have not studied symplectic geometry, it will probably feel like it is a very random question to ask. But I will ask it anyway, because the answer is quite beautiful. So let me ask a rather vague question, but I promise there is some motivation for it. Okay, so given some element, let's call it A, in O lambda, all I know is that the eigenvalues of this matrix is exactly this list. But I don't know very much more. Well, I don't. That's exactly what I know. So the question that I want to ask is, what do we know about the diagonal elements, the diagonal entries? Oh, so I'm sorry, I should introduce some notation. I apologize. So let's just say in the usual notation Aij. Yeah, so A is A sub ij, and it's an n by n matrix, so I have these n matrix entries. So the diagonal entries, of course, I'm talking about A11, A22, etc., up to ANN. Okay. All right, so there is a question. Okay. Very vague, I understand. But let me the reason I say this is because I wanted just the excuse to give this following precise answer. Okay, here's a theorem. So it's an old theorem. Oops. Sorry, I can't spell. Schur. There we go. And Horn. Okay, it says the following. The image of the map which associates to a particular matrix A in here to its diagonal entries, the image sorry, I hope the notation is clear. I'm just taking the matrix and I just forget everything but the diagonal entries, is a convex polytope. Okay, so that is coming into here as well. Somehow out of this geometric or linear algebraic situation, out just pops a polytope. Okay, that's a combinatorial object. In fact, I'm not done with the statement. In fact, with vertices, oh, and I guess while I'm writing there, I should erase this board. Okay. So the image is a convex polytope, and in fact, I can tell you exactly what the vertices are. With vertices, the n factorial permutations of lambda. Okay? So what am I trying to say here? I'm trying to say that within O lambda, there is a particular subset of very special matrices. They're exactly the diagonal matrices. And of course, this one is diagonal. But if I'm allowed to permute by an arbitrary unitary matrix, then of course I can permute the eigenvalues wherever I like. And so there are n factorial very special matrices sitting inside of O lambda. It's just exactly the diagonal ones. And I am telling you that, well, Schur and Horn tell you that the image of this map is in fact exactly the convex hull of the images of those particular special matrices. Okay. All right. So what I want to tell you now, which is part of this picture that I just erased, is I want to tell you how to think about this theorem in what a symplectic geometer would call the appropriate context. So to see this theorem in the appropriate context, I need to tell you some more terminology. Okay, all right, so here we go. Okay, so colon. All right, so here are some facts. are not necessarily hard, but today I will just tell them as facts. Okay, so first, one is that these O lambda are, so I already said they're homogeneous spaces of Lie groups, so of course they're smooth manifolds, but in fact they're symplectic manifolds. Okay, so what does this mean? Okay. Okay, so first of all, before I say about this, what I will do is I will actually write down the formula for you, but before I do that, let me just say, in fact, so what I told you here is for the unitary group. I just want to say here that the statement that I just wrote here is more general, so let me just say that first. Okay, so for G being the unitary group, of course, curly H is the set of Hermitian matrices. Is isomorphic, of course, to I times the skew Hermitian matrices, and that's, of course, exactly the Lie algebra. So that's supposed to be a curly small u. That's just the Lie algebra of the unitary group. And so really what I'm doing here is I'm looking at a certain the orbit of the unitary group under the usual adjoint action or the coadjoint action on its own Lie algebra. So that's one statement. Is the G orbit, okay, so I'm in the unitary case. So it's the UN orbit of lambda with respect to the usual coadjoint action, period. Okay? All right. So the symplectic structure. So first of all, I should tell you what is a symplectic structure. So a side, okay, a symplectic structure on a smooth manifold M. I'm sorry, I should give it a name. Omega on a manifold M is a closed, in other words, D of it is 0, non-degenerate, two-form, a differential two-form. Okay, so that's just the definition. So when I give you something, you should just check that it's a non-degenerate and that it's a two-form and so on. Now what I want to show you is I just want to show off the fact that in this Lie theoretic context, in fact, this is not a mysterious object at all. I can actually just write down for you what is the formula for this two-form in purely Lie theoretic terms. So again, just to emphasize one more time, I want to show off how easy it is to actually say that it's symplectic. So let me do this. Okay, so for these orbits of G, okay, let's see, the standard, so when I say standard, I mean there is one that is agreed upon that everybody uses. It's called the Kostant-Kirillov-Seryov symplectic form. Is given by the following formula. And once again, I'm not trying to do anything except just to show you that it is a very elementary formula. Okay? Okay, so omega sub KKS, Kostant-Kirillov-Seryov. Okay? So please remember, I'm thinking about the quadrant orbit. So suppose I have some element, some point on this orbit. Now please remember this is a homogeneous space, so G is acting transitively. So any tangent vector, I should be able to obtain it as the result of acting by some Lie algebra element. So my notation here will be, if I have a Lie algebra element X inside, for example, the Hermitian matrices, then the tangent vector that it generates when I act by that direction in the Lie algebra, I will denote that with a sharp. And then just to remind you that I'm at this point in the manifold, I denote with x sub c. Okay? So, once again, because I'm on a homogeneous space, any two tangent vectors have this form. I can have some Lie algebra element x and some Lie algebra element y, such that, in fact, the tangent vector is generated by the action of that Lie algebra element. Okay? So if I can tell you what this is, then I have told you precisely exactly what the two form is. Now, here's my point. In fact, by definition, this is given by this. Now, this is the usual Lie bracket in the Lie algebra, and now here I'm thinking about C as being, so there's two different ways I can do it. If I'm thinking about it in the dual of the Lie algebra, then it's just eating a Lie algebra element. If I don't want to do that, then I just pick a G-invariant metric and I pair this with that. Okay, but in any event, the point is, I have said nothing about manifolds or smooth structure or anything here. This is just a purely Lie theoretic computation. Okay, so that's the emphasis that I want to make here. Okay, very good. Now, the next thing that I want to say is, well, as I've been emphasizing this whole time, these symplectic manifolds are homogeneous spaces. There's a large group acting on them. And so in particular, any subgroup of G also acts on these orbits. So what I'm trying to say is this whole setup of this blackboard and that blackboard, the whole setup is equipped somehow naturally with large group actions, with a lot of symmetry. So G, so any subgroup also acts. So let me just re-emphasize what I just said. In particular, the geometric setup is hardwired, if you like, to have a lot of symmetry. Okay, we will come back to that later. And then finally, let me just make the note that I have said many times. In fact,
is it a GUN or what is
yes, okay. So here let me say everything for UN, but now my note is, in fact, everything I have written is valid for any compact Lie group. So everything so far, so in fact, the theory works in general. Even though I have told you for UN, in fact, everything I've written works in general for any compact Lie group. Okay, very good. So that's several facts. In fact, I listed them all as one, but okay. Two is this. This map phi, which I would completely understand if this is your first time to see it. You will think that is a very random, ad hoc map. Why would we consider this at all, and so on. So I would be very sympathetic if you thought that. But now I want to tell you, in fact, it is not an accidental or a random map at all, at least if you ask a symplectic person. In fact, phi is what is called, phi, so I'm sorry, I should remind you. So phi, this map from O lambda to Rn above, is in fact a so-called moment map. It is in fact a so-called moment map. Okay? For what? So moment maps are for some action. So which one? Well, now this comes back to my comment that I made 5 minutes ago. It's the moment map for the action not of all of G, but rather of the action of the diagonal subtorus that sits inside of here. So let me write this. For the T action on lambda, where T is the diagonal subgroup of UN. Okay? Very good. Okay, so well, that's not fair at all. That's not fair for me to write this if I don't tell you what a moment map is at least. So let me do that. Okay, okay, aside. What is a moment map? So what I'd like to now convince you of is that's not in any way a difficult thing either. It's actually coming just from this magical word. It's non-degenerate. Why is that so useful? Well, I want to tell you now why it's so useful. You see, since omega is non-degenerate, then, well, I have a 2 form on a vector space, right? For every tangent space, I have a way to pair 2 vectors and get a number. That's what it means to be a differential 2 form. And it's skew symmetric. So I have a skew symmetric form on a vector space. It's non-degenerate. So therefore, I have automatically, just as in the case of an inner product, yeah, I automatically get a map from V to the dual. Okay, so we get a map at any point. So this is just, I'm sorry. So this, when I'm writing here in the square brackets for a general symplectic manifold. So if I have a point P inside my manifold, then what I get is an identification, which I guess I would call omega tilde, from TP to its tangent space. And because it's non-degenerate, just like for an inner product, it is an isomorphism. Sorry, that doesn't look like it. Okay? Why is that so useful? Well, here's the idea. The fact that these are all isomorphism leads to the following identification. Okay. Well, let's see. So if I have a differential 1 form on M, by definition, what is that? That's a section of the tangent dual bundle, right? And so since I have this identification, this omega tilde automatically tells me that I have an identification between differential 1 forms and vector fields. Okay, that's just because at every point, if I have a 1 form, that's just an element of the dual space, well, omega tilde just tells me how to give a tangent vector. Okay, but then, just usual calculus says, the exterior differential D gets me a map from smooth functions on M to the differential 1 forms. Okay, so what the symplectic structure is telling me is that there is a link between this and that. Of course, it's not exact. It's not an exact correspondence because this has kernel, but there is this tight relationship. Okay, so e.g., what does this tell me? Well, it tells me the following. So, e.g., for G, a compact, and I will say here connected, Lie group, right? And if I take X to be an element in the Lie algebra, okay, then I can ask the following. It can be, well, what can I say? It can be possible, so I will say the word can, it may be possible that we have the following. Let me write this side first. So I'm following my notation that I introduced over there. This is, by definition, the vector field on M generated by X. I hope that's clear what I mean. I have the exponential 1 parameter subgroup sitting inside of my compact Lie group corresponding to this direction in the Lie algebra. And I just take derivatives everywhere for every point in the manifold and I get a vector field. And now, so given by this correspondence right here, it could be that there's actually a function on the manifold such that when I take d of it, I get a differential form. When I take only a tilde of it, I get that vector field. So it can be that I have this. Now, once again, I emphasize this is not necessarily always true exactly because D is not an isomorphism. Right? But it can be that it occurs, and when it occurs, compatibly with the group structure, we say that these functions together form a moment map. Okay, so that's why it's just the magic of the linear algebra coming from the non-degeneracy. The moment map is a very natural thing. So when such exists for all x and we say that the G action is Hamiltonian. Okay? And we organize all this information into a single map phi from, M to G star, such that if I just pair with the x, then I get the corresponding component. Okay, I just wrote a lot and said a lot. So let me pause and take a step back and emphasize one more time that although I spoke very fast and wrote very fast, the moral that you should come away from this board and a half is the following. Please remember multivariable calculus, which we probably all of us, well, I guess I don't know at KAIST whether you do this, but certainly at Berkeley, when you're a graduate student, you are a teaching assistant for multivariable calculus. Does this happen here?
Yes.
Yes, okay, all right. So you have all been teaching assistants for multivariable calculus, and you have taught the first year undergraduates, maybe second year undergraduates? I don't know. Anyway, you have taught about gradient vector fields, right, in just Rn, yeah? You have a function on Rn, you have the inner product on Rn, and you think about gradient vector fields, yes? You've all done this. All that I am saying here is you are doing exactly the same thing, except instead of using a symmetric inner product, you're using a skew-symmetric inner product. This is the only difference. Of course, this okay, so I try to make it sound trivial that it's the only difference. Of course, in terms of the geometry, it can make a huge difference whether it's symmetric or skew-symmetric, and that is why Riemannian geometry is different from symplectic geometry. Nevertheless, just for understanding what I'm trying to say here, I really want to emphasize you are just doing the same thing that you always do. If I have a smooth function, I take the differential, and I get some vector field. This is the correspondence, and usually in multivariable calculus, you put here the inner product identification. Instead, I'm using the symplectic structure, which is skew. But other than that, it's the same thing. So therefore, in the symplectic language, we often say that that this vector field is nothing else than the symplectic gradient vector field of this function. Yeah, in exactly to make the analogy with the Riemannian gradient field exactly, yeah, the language is the same. Okay, so that is all that is happening here. Okay, very good. But now I want to come back. Okay, so this was general symplectic geometry. Please now allow me to come back to this flag example. So now coming back. Okay, so now back to flags. Okay, so first of all, okay, let's do the example where n is 3. Oh, I'm sorry. So here I should say what I'm thinking about is this O lambda, where the lambda I are distinct. Okay, so let's think about n is equal to 3. In this case, lambda would be lambda 1 greater than lambda 2 greater than lambda 3. Yes? I'm assuming distinct. Okay? And then these special matrices that are diagonal, well, there are how many of them? There are 6, 3 factorial. So the 6, which is to say 3 factorial, matrices obtained by permuting the diagonal, yeah, so I just have lambda. Okay, so maybe instead of lambda 1, I have some sigma 1, lambda sigma 2, lambda sigma 3, according as to whether, so if I just take some permutation sigma in S3. Yeah, they are in O lambda, and this is my point. This is the point of what I want to write, and in fact, they are precisely. And this, if you are bored with what I'm saying right now, you can just check that this is true. Okay, they are precisely the T fixed points. Of O lambda. Please remember, we just got done saying some time ago that O lambda has an action of this torus, diagonal torus T, and I'm just claiming right now that these particular ones are precisely the fixed points. And so now, finally, after so many boards, I can tell you how you should understand this previous Schur-Horn theorem. Okay, so the Schur-Horn theorem. So now, after all that, I can now tell you the following. Okay, the Schur-Horn theorem is in fact a special case of the following famous theorem of Atiyah and Victor Gilliman and Shlomo Sternberg, okay, of the Atiyah and Gilliman-Sternberg theorem. So just in case, so just some history. The reason it is written like this is because Atiyah and Gilliman-Sternberg proved it independently, but almost at the same time. So that's why it is called Atiyah, Gilliman-Sternberg, but they are in fact 2 separate papers. Okay. Anyway, the Atiyah Gilliman-Sternberg theorem, which states the following: if I have a symplectic manifold with a torus action, compact symplectic manifold with a compact torus action, and now let me simply assume that this situation happens, that it is Hamiltonian in this sense. Okay, so I will write it this way. Be a compact Hamiltonian, so this is the language, Hamiltonian T-space. So just now, I'm sorry, I realized I didn't introduce this terminology, but it is very simple. We say that the action is Hamiltonian, and if the symplectic manifold has an action which is Hamiltonian, we call it a Hamiltonian T-space. So I'm sorry for that. Anyway, but it's a compact Hamiltonian T-space. Okay, then, please remember what we wrote earlier. We just said that the image under phi of the so O lambda, so in this case, in just M, is nothing else than the convex hull of the images of the fixed points. That's the statement. Okay, so then phi of M is the convex hull. In particular, it's a convex polytope. Okay, so that is a much, much more general theorem. But anyway, I hope you see now that it's what we said earlier is nothing else than a special case. Okay? Now, so I should say again for historical remarks, this theorem is basically the origin. It basically starts everything in terms of modern symplectic geometry, in terms of its interaction with combinatorics and the combinatorics of polytopes, and essentially the equivariant geometry of the Millet map. So this somehow started everything. Okay. Okay. All right. Very good. Yes. The Schur-Horn theorem is much older, and I'm sorry, I don't exactly know. Sometime. So let's see. So yes. So the way I believe it works is Schur. I'm sorry, I'm going to probably get this wrong. So one of them proves that the image lies inside the convex hull, and the other proved that in fact everything in the convex hull occurs. And I'm sorry, I can't remember which is which, but they are different pieces of work. But now these days it is just called the Schur-Horn theorem to say that the image is exactly. But anyway, but yes, the Schur-Horn theorem was known much more in advance than the Atiyah-Gilliman-Sternberg. Okay, very good. Okay, so what I just said earlier is a historical remark that this theorem really started everything. It just told us that somehow the equivariant geometry of Hamiltonian T-spaces is a very combinatorial thing. It's somehow telling us to just, well, not just, but to focus on these fixed points. So the next chapter and what I want to say next, so the next goal, I can't remember if I numbered my goals, I'm sorry. Let me just say goal number 2 is I want to show you how, motivated by this big theorem of Atiyah and Gilliman-Sternberg, how people have started using the Mowat map really as a tool to understand equivariant topology. So my goal number 2 is to let's see, so let me say this, the equivariant Morse theory of Mowat maps. Well, okay, not necessarily cohomology, just equivariant topology in general. Okay? So this is what I want next to discuss. Okay, let me just see what I can do, okay? All right, so, when should I stop? Soon.
4:30.
4:30? No, I should stop at 5?
5:30.
Okay. All right, so let me see if I can let me see what I can do to convey the picture here. Okay, so again, let me not rewrite it. As above, let me allow m, omega, and phi to be this notation for a Hamiltonian situation with a Mowat map. Okay, then here's a fact. Okay, this is not a hard fact, but I don't have the time to prove for you. It's very easy, in fact. It is, in fact, generically true. If I choose an appropriate element in the Lie algebra, then what will happen is, if I look at this particular function for that choice of the Lie algebra, so please remember one more time, the whole idea was that I can encode somehow the action of this torus just by using these functions, yeah? So now I look at a particular choice of such a function, and I look, well, it's a function on a manifold. You're a topologist. What do you do with a function on a manifold? You try to do Morse theory, of course. And so the first thing you do is you look at the critical points. Okay? And now a fact is, the fact is that this is nothing else than precisely those fixed points that were so important for you in the Atiyah theorem. Okay, so once again, let me emphasize, this is not a hard statement. But again, I just don't have time to justify. But it is a basic thing. So what I'm trying to say here is that this immediately tells you that there's a relation between the Morse geometry, if you like, of phi and the T action. Okay, so that is a very vague statement, so let me try to make this more precise. Okay, so more specifically, okay, what I mean is as follows. So, I'm sorry, there's some technical things I should say. Here, I really do need that T is abelian, and in the Atiyah theorem also, it's very important that T is abelian. Since T is abelian, okay, the adjoint action of T on its own dual of the Lie algebra is trivial. It's just because it's abelian. Please remember, the adjoint action is always conjugation, yeah? If it's abelian, that's nothing. So it's a trivial action. Why does this matter? Well, it's because that implies that this mode map phi is in fact a T-invariant map. Constant on T orbits. Okay? In particular, that means that phi x is T-invariant, which is, say, every component is T-invariant. What that means, if I pick, so T here is a compact torus. It's a compact group. I can always pick on any manifold an invariant metric with respect to a compact group just by averaging. So let me just do that. I just take an invariant metric on M. And if I think now about the normal gradient flow, not the symplectic gradient flow, I'm just doing normal gradient flow now. I'm doing normal Morse theory. Okay, so if I do ordinary, so the usual gradient flow, so again, I emphasize, that's in the usual sense, okay, Riemannian geometry sense. Gradient flow with respect to this particular function, okay, please remember, I'm just trying to do Morse theory, okay, gradient flow with respect to x, okay, so here, just for technicalities, I should remind you with this, I'm going to assume, without loss of generality, that I take a T-invariant metric to begin with, okay? Now that gradient flow, what is that? That is an R action, yeah, on the manifold. And I already have a T action, and I claim that it's not hard to see that this is in fact equivariant. Okay? Pant. What does that mean? That means that so what do you do when you do Morse theory? You look at the Morse flow up or the flow down cells, whichever you prefer. And the fact that the gradient flow is T equivariant exactly tells you that the Morse flow up or flow down manifolds are actually invariant. Okay, so what does this buy you? Well, okay, so the title of my talk was A Symplectic Perspective on Schubert Calculus. I haven't mentioned Schubert Calculus in a while, so I will do so now. Okay, so all of this nonsense, all of this stuff, for example, gives me that I can get, in fact, a Morse theoretic interpretation Morse theoretic interpretation of Schubert varieties. So these are particular subvarieties in the flag manifold, or if you like, in the orbit of G, O lambda, but instead of trying to define Schubert varieties, because I don't have time, let me just try to draw an example, which I hope is illustrative. Okay, so here's the example. So pictorial example. Okay, so let's look again at O lambda flag C3. Okay, so I had a picture up before, I think, but maybe I erased. Okay, so let me just draw in a particular way. Okay, sorry. Okay, so I'm actually going to label. Please remember, the 6 points here are supposed to correspond to what? They're supposed to correspond to these special diagonal matrices obtained by just permuting the diagonal elements. So I can parameterize them by just writing down which permutation I use, yeah, to permute those diagonal elements. So I will do that. Okay, so here's the identity E. Here's S1. Here's S2. I'm sorry, I should say S1 is the simple transposition which transposes 1 and 2. 2 is the transposition exchanging 2 and 3, etc. But anyway, let me write them. Okay? All right, so now, what do I mean by more slow up, more slow down? What's the Schubert variety? So an example is if I pick this fixed point. I'm sorry, I forgot to say something very important, I apologize. Okay, so what are we looking at right now? We're looking at the image of the T moment map. That's what I told you earlier. Please remember, the Atiyah-Gilman-Sternberg tells us that the image of the moment map is nothing else than the convex hull of the fixed point, the images of the fixed point. So we're just staring right now at the T moment map image. In particular, I should think of the blackboard as being the vector space T2 star. Okay? Now, if I look at a particular component, that should mean that, so I'm using an invariant metric, etc. That should mean I'm just looking at some projection of this blackboard to a one-dimensional subspace. And the way I have drawn it, I want you to think about the projection as being just the vertical line, and I just project to the vertical line. In particular, this is the minimum. I have arranged it so that the identity is the minimum, and the maximal var group element is the top, the maximal. Okay, so I'm sorry, I forgot to say that. Okay, so now if I look at this particular fixed point, then if I want to say Morse flow up, then I can draw for you the Morse flow up, and you will see yet again that it's actually a combinatorial object. I will get a subpolytope. It's this. Right there. Okay? So I'm sorry I can't justify this for you in the time that I have. The idea, however, locally, the idea is as follows. If I look at the fixed point here, and I think about the T action just on the tangent space there, then that T action on that tangent space to this fixed point is in fact encoded just by weights, the T weights of a certain representation. It just decomposes into one-dimensional weights. And the magic of a moment map is exactly that. The way I have drawn the edges exactly tell you what those weights are. They're just the direction of the edges, the way I have drawn them. That's just magic of moment maps. It's not hard, but it's very convenient. And then to say what is the flow up, you should simply say, okay, which of these arrows point up with respect to the direction that I've chosen. And that's all. And so it's not too difficult to see from this point of view that, okay, so I should just take, so locally I know I should just take this piece, and then it just fills it out the way I have shown you. Okay, so that's an interpretation. Okay, very good. So now I should just finish because I have only a few minutes. So what I will do is draw the one last diagram then. To just conclude in terms of what I've been trying to show you. Yes? I'm sorry.
The Schubert variety.
Yes.
The Schubert variety should be corresponding to S1.
Yes.
Should be the inverse symmetry.
Okay. So I'm getting an excellent question, which is, I drew this in pink, and I treated it as if it should be absolutely obvious what I mean. But of course it is not. What I have drawn is something on the image. And so Professor Sa is asking, so what do you do now to get the Schubert variety? Is it just the pre-image? And it's not quite the pre-image. What I am saying when I draw this pink subpolytope is that the image of the Schubert variety is this. But it's not the same as taking the pre-image. Yeah, exactly. The pre-image is more than the Schubert variety. And that's not too surprising because the Schubert variety is smaller dimensional in the tonal space. Yeah, but the image is this. Okay, so let me now finish by drawing one more diagram and then maybe just saying quick words. So what I have shown you in the past maybe 50 or so minutes is the following. So So in general, what we have is a T action on some orbit of a Lie group, which acts, T acts on it, and it has a moment map. So that's the geometry vertex. This is the algebra vertex. And the combinatorics vertex is the image. Yeah, because please remember, this is just the convex hull of the images of the fixed points. Okay? In fact, a little bit more combinatorial information is actually encoded precisely because of what I was saying earlier about the magic of the moment map, that it actually tells you, in fact, something about the isotropy representations as well. So there's actually a little bit more information than just the images of the vertices, but let me not make too much out of that. So what I was able to do, I hope, is to indicate for you something about this arrow. And now let me say, just simply in words and not try to say do more. In fact, this kind of situation where I use more information, just not just the edges but also the moment graph, then in fact there exists a theory. So it's usually called GKM theory that goes from the moment graph to a computation of, okay, so here, oh, I did put T, very good. Okay. Yeah, so one can go from here to here, just in the same way that I have just shown you, you can go from here to there. And I'm sorry, I have not had time to tell you so much about this, but anyway, all the vertices are connected in this very concrete way. So thank you very much for your attention.